Hi all. In the last class we have completed section 9 by introducing the interesting subgroup AN alternating group of the symmetric group of Sn. And for example, we consider n is equal to 3. We know that S3 contains 6 elements, say rho naught, rho 1, rho 2, mu1, mu2, mu3. So these are 6 elements of S3, or we have another notation or symbols for these rho naught, rho 1, rho 2, etc. So rho naught is identity, and rho 1 can be expressed as 1, 2, 3, cycle 1, 2, 3, and rho 2 is 1, 3, 2. So these two are 3 cycles. Then we have 2 cycles, 1, 2. Then mu1 is in fact 2, 3 because 1 is fixed in mu1, so we write this is 2, 3, that is mu1. Though there is no ordering in this and ordering for the elements of the set, we write mu1 first. This is 2, 3, and mu2 is 1, 3, and 1, 2 is our mu3. Okay, so these are 6 elements. We know that the first element has order 1 because it is an identity element, and the next two have orders 3 each because these are 3 cycles, and rest of them have the order 2 because those are 2 cycles. So if we consider the even permutations in this S3, we can see that these are a product of one transposition. So and the expression of these permutations and the expression of these permutations has only one transposition. So if we consider these 3 cycles, then we can easily write 1, 2, 3 as 1, 3 times 1, 2. Okay, so this product is same as 1, 2, 3. So we can consider this as a product of 2 transpositions or 2 cycles. So this belongs to N, okay, or A3. Obviously, rho naught is an identity element. We know that identity element is always an element of N. So or A3. So we write this rho naught belongs to this, and 1, 2, 3 belongs to this one, and similarly 1, 3, 2. 1, 3, 2 is nothing but 1, 2 times 1, 3. So this again product of 2 transpositions, so it's an element of A3. So if we consider S3, then we know that S3 has 6 elements. Then we come to this A3, then A3 should have 3 factorial by 2, that is 3 elements. So these 3 elements constitute A3. So we write this is A3. A3 consists of rho naught, the 3 cycle 1, 2, 3, and the other 3 cycle 1, 3, 2. So these 3 are the elements of A3. Okay, in a similar fashion you can write A4, A5, etc. Anyway, any n will have n factorial by 2 elements. Okay, so this is in fact the largest proper subgroup of S3. Okay, we know that the subgroup of, we will also see in this session, session 10, Cosets and theorem of Lagrange. In the session we will discuss cardinality of the subgroup divides the cardinality of group. So the maximum, the largest value which divides the cardinality of S3 is n factorial by 2. Okay, so the largest value less than n factorial. Okay, that means if you consider 6, that is 3 factorial, then when you consider the divisors of this, 1, 2, 3, 6 are the divisors. So this 3 is the largest possible value which divides 6 and which is less than 6. Okay, so that is the maximum possible. After discussing the theorem of Lagrange, we can see that this is the largest possible order of the proper subgroup of a group. Okay, so these ANs are the largest proper subgroup of SNs. Okay, so we will discuss in this. In order to discuss the theorem of Lagrange, in section 10 we will discuss cosets. Okay, so first of all we define cosets. For the coset we consider the same subgroup. The coset is defined for subgroup of a group G. So for example, if you consider A3 as the subgroup of S3, Okay, we know that A3 has these 3 elements and S3 has 6 elements. Okay, how will you write the coset of A3? Coset of A3 of A3, which is a subgroup of Sn. So we write coset of A3 in S3. So this is the way we represent this cosets, or we write this coset. So these cosets are nothing but the partitions of S3. Okay, so if you have S3 here, so we know that this is S3, and if we have A3 here, A3 consists of row 0, row 1 and row 2. Okay, now you consider any element from S3. You know that if you choose any element from this A3, and if you choose row 1 belongs to A3, then operate row 1 with all these elements, that is row 1, row 0, row 1, row 1 and row 1, row 2. You know that this since this A3 is a subgroup, this set is nothing but row 0, row 1, row 2, because the subgroup A3 has closure property. So when you operate any elements together with these elements of S3, then we will get the A3 itself. Okay, but if you choose, we cannot assure that if you choose an element from this, okay, say sigma, if you choose a sigma from this side, we cannot assume that rho 0 sigma is an element of A3. Okay, when you apply the sigma with the elements of A3, then that means sigma rho 0, sigma rho 1 and sigma rho 2. Okay, we cannot assume in general that these are elements of A3 itself. So this is need not be. This need not be elements of A3. So for example, if you choose this element, this 2, 3 is element sigma, then what is sigma times, if sigma is equal to 2, 3, then what is sigma times rho 0? Sigma times rho 0 is, since rho 0 is identity, sigma times rho 0 is rho 0 itself. So that is 2, 3. Okay, then what is sigma times rho 1? Sigma times rho 1 is sigma times that is 2, 3 times rho 1. Rho 1 is 1, 2, 3. When you multiply this, you can get the image of 1 from this is 1 is mapped to 2 and 2 is mapped to 3. So ultimately 1 is mapped to 3. When you observe the image of 3, 3 goes to 1 here and 1 is fixed here. So 3 is mapped to 1. So this completes. Okay, and we know that 2 is fixed in this product, because 2 goes to 3 and that 3 goes to 2. So ultimately 2 goes to 2. So this sigma rho 1 is nothing but 1, 3. Okay, similarly if you evaluate sigma rho 2, you will get 1 plus 1. So we know that these are not all elements of this A3. Okay, so we cannot expect these are elements of A3. That means this need not be an element of A3. So, but if you consider these elements, that will give another set. Instead of rho 1, rho 1, rho 2, we can get another set. Say this is mu1, mu2, mu3. Okay, so this set is called the coset of A3 with respect to sigma. Okay, that means if you consider a sigma belongs to S3, then if you have a subgroup A3, then operate sigma to all the elements of A3 from the left. So this set is nothing but sigma times rho 1, rho 0, sigma times rho 1 and sigma times rho 2. And this set is called a coset. Called a coset of a subgroup, the subgroup S3 in S3 with respect to the element sigma. Okay, so this sigma A3 will give, what is sigma A3? Sigma A3 will give these elements mu1, mu2, mu3. So these are sigma A3. Okay, now you consider another element, say the sigmas, since the sigma is 2, 3, we can write this as 2, 3 times A3. So this is nothing but mu1, mu2 and mu3. Okay, similarly you can consider 1, 2 times A3. Okay, 1, 3 times A3 as well. So if you evaluate all the elements of this, you will get the same set. Okay, so first of all you evaluate 1 2 times A3, that is 1 2 times rho naught. 1 2 times rho naught is rho naught itself, sorry 1 2 itself, that is our mu 3. Okay, similarly you can write 1 2 times rho 1. What is rho 1? Rho 1 is 1 2 3. So what is the image of 1 here? 1 goes to 2, 2 goes to 1. So 1 is fixed, then this will be, and we can evaluate the images of other two. So we can get this as since 1 is fixed, then the other two will be 2 3. Okay, so 2 3 is nothing but our mu 1, and finally we will get mu 2. Okay, similarly you can get when you evaluate this, that is mu 2, and you can evaluate mu 2 times rho 1. Mu 2 is 1 3 times rho 1, that is 1 2 3. So this will be, when you operate this, you can get 1 goes to 2 and 2 is fixed. So 1 goes to 2 here, and 2 goes to 3, 3 goes to 1. So this is completed, and 3 is fixed in this expression. So you will get 1 2, that is mu 3 and mu 1. Okay, so moreover we can see these cosets. You can evaluate rho naught times A3, so that will give A3 itself, because A3 has closure property, and rho 1 times A3, that will again get A3 itself because of this closure property. Similarly rho 2 A3 is equal to A3 itself. Now you evaluate the other cosets using sigma. First of all we write 2 3, so 2 3 times A3. 2 3 times A3 is nothing but mu 1 mu 2 mu 3. Okay, similarly 1 2 times A3, so this will give again mu 1 mu 2 mu 3, the same set mu 2 mu 1 mu 3. Similarly 1 3 times A3, so that is again mu 1 mu 2 mu 3, mu 1 mu 2 and mu 3. So when you consider these cosets, these are the all possible cosets of A3. When you consider all these cosets, you can see that these cosets, so these are A3 are all same in this case, and in the other case we will have mu 1 mu 2 mu 3. So we can say that there are two distinct cosets of A3. One is corresponds to this, and next is corresponds to this set, that is mu 1 mu 2 mu 3. But once you write the cosets of this A3, okay, so this is set of all cosets of A3. So that is nothing but A3 comma the set mu 1 mu 2 mu 3. This set of all cosets, the union of all cosets is nothing but our whole group S3. So that means A3 union, when you observe this, A3 union mu 1 mu 2 mu 3 will be our S3, the whole group S3. And you know that these two, since these are all same and these are all same, and when you consider distinct cosets, one from this and one from this, so then these cosets will be disjoint. Okay, distinct coset will be disjoint. Cosets will be disjoint. There will not be a common element in both. Disjoint. Okay. So now we classically define what is a coset of a subgroup of a group. So in general, we will be enabled to define coset if we define some relation, or if we discuss some theorem on this. So first of all we can discuss a theorem. Okay, this theorem gives a equivalence relation in a group G corresponding to a subgroup. Okay, that means let H be a subgroup, of a group G, and define a relation. That relation is denoted by, the relation is denoted by this symbol, tilde sign suffix L. Okay, be defined by A is related to this B if and only if A inverse B belongs to H. You can easily prove that this is reflexive, okay, because A inverse A, so that is equal to identity, which is always an element of a subgroup. So this implies A is related to A. Okay. Similarly, you can observe the symmetric behavior, that is A is related to B. Then we have A inverse B belongs to H. Okay, but we know that H is a subgroup, hence the inverse of this element is also an element of H. So A inverse B whole inverse is also an element of H. What is A inverse B whole inverse? That is B inverse A inverse inverse, that will give A. Okay, so this is an element of H. So then consequently we can get B is related to A. Clear? Similarly, you can prove the transitivity, A related to B and B related to C. Then we have A inverse B belongs to H and B inverse C belongs to H. Okay, then its product is also an element of H. That means A inverse B times B inverse C belongs to H. That is A inverse C belongs to H. That implies A is related to C. So from this you can say that this relation is an equivalence relation. Okay, so this relation gives a partition for the whole group G. Okay, so first of all you observe the equivalent class of this relation, the equivalent class of A. So if we choose A belongs to G, then you can consider the equivalent class. I denote equivalent class of A as this. So this is set of all X belongs to G such that A is related to X or X is related to A. If you observe all these elements, then you can see that this X takes the form X belongs to G such that A is related to X or X is related to A means this A inverse X is an element of that A inverse X is an element of that H. Okay, so this is nothing but set of all X belongs to G such that A inverse X equal to H for H belongs to H. Okay, what is this set? This set is nothing but set of, we can replace this X in terms of A and H. Okay, so A inverse X equal to H means by operating A, pre-multiplying A to this equation, you can get X equal to H. So this is nothing but A H such that H belongs to H. Okay, so this set, this equivalent classes are called left cosets. Okay, so once you prove this theorem, theorem 10.1, you can see that the equivalent classes of each of the elements A. Okay, that consists of set of all A H such that H belongs to H. So these are called cosets. Cosets of H in G with respect to A. With respect to A. Okay. So in a similar fashion, you can define another relation that is called A is related to, this is denoted by this symbol, A is related to B, if and only if that can be related using A B inverse belongs to H. Okay, this is also an equivalence relation. So you can repeat this process, then you get to the cosets again. So those cosets are called right cosets. Okay, so in fact these cosets are called left cosets. So left cosets are obtained by applying or operating the element A to the left of every element of H. So if you observe this, then you can say that the equivalent class corresponding to this relation is nothing but set of all A such that H A where H belongs to H. So this will be the equivalent class corresponding to this relation. Okay, so this equivalent classes are called right cosets. So now we can define left cosets and right cosets of a subgroup H in G. Okay, so please go through the section 10, the first parts of section 10 up to examples of cosets, that is up to 10.7 is also describe some examples. Okay, so please go through the section, the first part of this section 10. Okay, so in the next class we will discuss what is Lagrange's theorem. Okay, thank you.